as an energy versus a larger denomination that I talked to you about, like getting a $5,000 bill versus a $10 bill. I think I used that analogy in another class. So let me talk to you about that for a second. Why is ATP such a useful storage? So ATP, every time you burn a molecule of ATP to make ADP plus inorganic phosphate, you get an energy payoff of about negative 7.3 kilocalories per mole. Okay, so that's not a lot, that's not a lot of energy really. It's like 7.3. But what it is, if you think about it, if I paid you, say you made $5,000 a month, my full salary. If I gave you a $5,000 bill, could you go use that very easily? No, nobody's got change for that. It's not a useful denomination. But if I gave you a bunch of 20s, that's kind of useful. I can use a 20 here, a 20 there. And it's the same idea with ATP. We could store that energy in a molecule that all the energy was stored in one big molecule, but then you have to burn the whole molecule to buy anything in the cell. And so a lot of the cellular work, it's like, okay, I need 10 kilocalories here, 4 kilocalories there. So this is kind of an appropriate denomination where you can pay for a lot of different energy uses in a good sized bill, a good sized denomination. So this is like a $20 bill, very useful in the cell. $500 bills, less useful. Okay, so you get a bunch of ATPs, but it wouldn't. Again, we don't want our bills, our denominations to be too small. So what if we stored energy? You only got like 0.5 kilocalories per mole. That would be like me giving you $1 bills as your paycheck. Again, that's too bulky. You can't even fit all that in your wallet. You have this huge wallet sticking off your rear end because you have $5,000 $1 bills. So that's not useful either. The cell needs something that's kind of that right mix where it's useful amount, it's not too bulky, but it's also not these $5,000 bills where you release too much energy to perform most of the work that the cell needs to do. Okay. So again, this is just a few summation points when you're studying. It's the energy that's stored in this concentration gradient that is used, and this concentration gradient is generated from all of those redox reactions. That's the energy is used to create this concentration gradient, and then when they fall down through that ATP synthase molecule, that's actually where they are doing work or rebuilding ATP molecules. The proton motive force is basically a term that we use to describe that it's the protons. Motive means like to motivate to actually do something. We're using those protons to actually do mechanical work. So we call it the proton motive force. Yes?
With that protein that attaches and turns it, is there a special name for that specific protein, or do we just need to?
It's called ATP synthase.
Okay.
And so just know ATP synthase and know the different parts. So there's a stator, there's a rotor, there's a knob, or there's a rod and a catalytic knob. So there's 4 different components to it. So just understanding it.
Okay, so is ATP synthase the name of the protein or the whole process?
It's the whole protein. Yeah, this is actually the name of the protein that allows the protons to fall back down into the mitochondrial matrix. And so the whole process is called it's chemiosmosis oxidative phosphorylation. So that's the process of turning the proton gradient into work, but this is the actual protein that allows that gradient to be converted into ATP synthesis. And then this is also just pointing out kind of, if you follow the molecule, the glucose, you get, when you think about most of the energy, this is not all the energy, because we're not talking about glycolysis and Krebs cycle here, but glucose gets broken down. A lot of that energy gets put on these electron carriers that get sent over to the electron transport chain. The electron transport chain generates a proton motive force that is then used to make ATP. So this is where most of the energy is coming from. And then this is just also pointing out about 34% of the energy in a glucose molecule is actually transferred to ATP. That means that the rest of it is given off as
heat.
Yeah, so 34% of it, you think, gosh, that's not very good. Only 34% of the energy actually gets used to make ATP, and the rest of it is just lost. But if you think about it, your most efficient engine, if you go buy a car, is able to convert about 25% of the energy stored in the fuel into energy that's actually used to move the car forward. So it's really not a bad kit. It's actually a pretty efficient little cell. And if you like to eat, it's good that this number is 34. Because if it was like 80%, then you could only eat like 200 calories a day, because you would eat, convert them very efficiently. And so if you like your meals and you like to eat, it's probably good that this is 34% and not 90%. And it's also pointing out, I told you that it's 30 to 32 molecules of ATP. It's not an exact science. And that's because, well, there's several different reasons. One of the reasons is, remember in glycolysis, we make a molecule of NADH, and then that NADH has to get sent into the mitochondria. So this membrane, this inner membrane, is impermeable to NADH. So the NADH can't really get sent in. So actually what happens is this NADH molecule has to give its electron, has to kind of pass its electron into the mitochondria and have another electron carrier grab it. And you don't know if it's going to be NAD or FAD. So NAD or FAD could snag the electron from the NADH molecule that we get from glycolysis. And if it's FAD, remember we don't get as much energy from that guy because he gives his electron at the second level instead of the top level. So we can't get as much energy as he will down the middle. So that, yeah, this is just pointing this out. So here's our NAD molecules that come off of glycolysis. And remember, we can't get this NADH molecule into the mitochondria. It's impermeable to NADH. So we basically have these electron shuttles. And so the NADH electron gets shuttled into the mitochondria, and it could go to an NAD molecule or it could go to an FAD molecule. And if it goes to NAD, we get the maximum amount of energy, FAD slightly less. Let's see. So that's one of the main reasons. That's the only one that I'll go to. Some of the others are a little bit too involved. But that'll be your main reason that we don't know the exact number. So it points out 26 or 28 ATPs for a total of 30 to 32 total. So most of it's coming from around stage phosphate. And so we'll stop there for the test. And then, so